everyone, welcome back. Broadly speaking, the lidars that we have discussed so far can be categorized in two main ways, right? Let's go over each of those one by one. The first category is through data modality. The output of the lidar can be a 2D data or a 3D data. So, remember from the previous section, we saw this the sensor, right? The sensor that emits a single beam of light and how it looks like. Now, imagine we put this single beam of sensor with the sender and receiver on a motor, and this motor constantly rotates. Um, what do you get? The distance that you will collect in such manner will look more like a line sweeping across the motor direction, much like this first image. To get a better intuitive sense, think of how an apartment floor plan looks like, right? Now take this same setup. Except for rotating just one single beam sensor, we'll stack multiple single beam sensors on top of each other. Maybe let's say 16, right? And now we rotate all these 16 vertically stacked sensor on that same motor. What do you think the data output will look like? You probably guessed it right. The bottom left image, where each of the 16 sensors, right, that are stacked on top of each other, sweep their own line, just like the 2D LiDAR. And together we see 16 vertical lines scanned across the environment. That's exactly how a 3D LiDAR works. You can see how each of these LiDAR look like in real world. This LiDAR has a vertical array of sensors behind the glass enclosure. Now, next classification or categorization of LiDARs can be based on the parts or how they're constructed. First one is mechanical type. The ones that we already saw with the motor rotating the sensors, those are mechanical ones. The second type of LiDAR in this category is called solid state LiDARs. They do not have any mechanically moving parts inside them, like a motor. Most commonly, the way they capture the world in 3D data is by flashing a 2D array of light pattern. Just think of like a flashlight, right? And how it will illuminate a section of the environment when you turn on the flashlight. Except for this flashlight is now an infrared flashlight, and each of the beam that is sent through this flashlight is read back by the lidar. So it kind of creates a distance array of the signal. Mechanical lidars typically have a larger field of view than solid state lidars because they are obviously rotating around the environment, right? On the other hand, solid state lidar are fast and they do not suffer from the same wear and tear of the motors in the mechanical lidars. So now that we have dived deep into understanding how lidars work, let's go over some of the popular application of these devices in real world. The most widely known and popular application of this technology is autonomous vehicles, as you may have seen on roads already. There are also about self-driving cars. LiDARs are commonly used to detect all kinds of obstacles and objects in the environment, like maybe lane markings, pedestrians, other vehicles like cars or trucks, and so on. This gives self-driving cars its ability to see the environment in 3D and navigate safely by avoiding collisions. The second popular application of LiDAR is in mapping and surveying. This can have many sub-applications. For example, topographic mapping. LiDAR is used in this field to create detailed 3D maps that represent the surface of the Earth, right? Including the terrain, the elevation, the vegetation, and other man-made features like maybe structures like buildings and so on. This can be crucial for flood monitoring, infrastructure development, and environmental monitoring. We can see in the image below how the elevation is shown by different color gradients. The second application in this category can be urban planning. In this field, it is used for planning new construction sites, assessing traffic patterns, managing utilities, or visualizing future development. This aids in assessing environmental impacts and future planning for sustainability. Another application can be Agriculture. LiDAR can map agricultural fields in high resolution, detecting maybe variation in crop heights and then the soil composition, water levels, and so on. This can help farmers a lot in optimizing the irrigation, making plans for their planting layouts, and also to monitor the health of their crops. Precision farming uses an array of sensors, including LiDARs. The last application in this category can be forestry and environmental monitoring, right? LiDARs can accurately measure tree height, maybe canopy density, and forest volume, aiding forest management and conservation efforts. Okay, so now we know what a LiDAR is and where they are commonly used, right? Let's look at the output it creates. It's called point clouds. What are point clouds? As the name suggests, it is a collection of points which represent 3D geometry of the environment we are trying to map. Right? Each point in this cloud represent a location where the lidar laser hit the object. Right? This point can have information like X, Y, and Z of that particular point, maybe intensity and color information as well. Okay, so if you have ever played the game Connect the Dots, you already understand this concept much better. In a point cloud, each point acts as a dot that, when combined with other point, creates this 3D structure or picture of the environment, right? When we have thousands or even millions of these points, we start to see patterns, right? We start to see more than just dots. These point together begin to form recognizable shapes of maybe buildings, trees, terrains, and other objects, just giving us an image of a whole arena in terms of dots placed at varying distance. Sample image here is of a city, right? Now this image is a point cloud of a city in India that we can clearly make out the bridge from the buildings here. How point clouds represent 3D space, right? Point clouds can vary depending on how lidar system captures the data. For example, we can have two kinds of point clouds. We can have a dense point cloud or we can have a sparse point cloud. Now, in dense point cloud, where millions of points are packed together closely, giving us a high level of detail, right? On the other hand, sparse point cloud have fewer points and is useful for general mapping rather than detailed object shapes. LiDAR continuous scanning is what generates these point clouds. Think of it as a LiDAR building 3D model of the world, one dot at a time. And each of these points in the cloud serves as a piece of that model. Now, combining the point cloud data with advanced algorithms, we can do a lot of things. We can detect, measure, or even classify different objects in the scene. Also, to give you a preview, let's watch this interesting video of an online application called Cloud Vision. This can help us understand how the point clouds, look like. Um, we will use a PL-Wi-Fi, which is a common extension for point cloud data. This is going to be a dense point cloud of a man's face, and then we zoom in to see individual points in it. As you can see, we can even manipulate the appearance of the points, making it from square shape to a circular shape. We can add color gradient to see contours better, change light, and so much more. So to conclude, in this session, we looked at different types of LiDARs. We also looked at their application and got an understanding of how LiDAR output data looks like, which is called as point cloud, and how they represent the 3D world around us. Now, so this concludes the module 1. In the next session, we will start with module 2, which is on basics of LiDAR annotation and understand the basic of annotation and along with different types of annotation. See you there.